Good afternoon, everybody. Hope you're all good and safe at home. Let us continue with our section of Hilbert spaces. Chapter 2, Hilbert spaces, section 2.2. We had a deal with the concept of the projection and how we can prove that a particular if we are considering any closed subspace or any separable space, the projection element exists and it is unique and all. And now what we are going to do is we are moving on to the concept of the orthogonal complement of a subspace. So we will be familiar with this term. Let's just recall it again. So let L be a subspace of the Hilbert space H. The orthogonal complement of L is given by the set L orthogonal or L perpendicular is equal to the set of all X element of H such that X is orthogonal to L. That is, L orthogonal is the collection of all the elements of H which is orthogonal to the space L. So by this definition itself, or by the property, we can easily see that the orthogonal set of any subspace of the Hilbert space will be closed. Okay, so let's see how we can move on to the proof of this. I mean, there is nothing much to prove. It is simple. We have to show that the orthogonal set or orthogonal complement is always closed. Now to show that a space is closed, what do we need to show? We need to show that if we consider any sequence, say let xn be any sequence in the space L. Okay, now if xn is a sequence, we need to show that if it is converging, if suppose xn is converging, suppose let us say the sequence xn converges to a point x. So to show that L is closed, we need to show that this x is also an element of L, right? So here this is how we show that a space, a subspaces or any given set is closed or not. So here what we need to show, we have to prove that L orthogonal is a closed space, right? So how can we show that L orthogonal is closed? We will first consider a sequence in L orthogonal. So let xn be a sequence which converges say as we have, let us suppose that xn converges to x. Now what we are going to show is we are going to show that x is an element of L orthogonal. So how can we see? Now as xn is a sequence in L orthogonal, we can say that inner product of xn and L will be 0, right? Why? Because xn is an element of L orthogonal, so it will be orthogonal to every element in the space L. So inner product xn L will be 0. Now let us consider the inner product x and L. Now if we get this is 0, we can prove that, or we can conclude that x is an element of L orthogonal. So if we consider the inner product xl, this can be written as x is chosen to be the limit of the sequence xn, right? So limit xn L. Now inner product was a continuous function, so we can take the limiting value outside. So this will be nothing but inner product, limit inner product xn L, and we know that inner product xn L is 0, so this value will be 0. So we get inner product xl is 0, so this implies x is an element of L orthogonal. So xn was a sequence in L orthogonal which was converging to the point x, and we obtained that x is also an element of L orthogonal. That is, every limiting point is contained in that particular set itself. So that's how we can see that the space, the orthogonal set of any subspace will always be closed. So now what we are going to do is, next we will move on to a theorem which states that the direct sum, okay, we all must be familiar with the term direct sum in algebra and all, so we are introducing that concept in this section also. That is, if L is a closed subspace of the Hilbert space H, then L direct sum L orthogonal will always be equal to H. So this is the theorem, that is L direct sum L orthogonal is always equal to H. Now let's move on to the proof of this theorem. How can we prove this theorem? So first let me say that by the definition of L and L orthogonal, it is clear that L intersection L orthogonal will be empty. Okay, it is clear by the definition of L and L orthogonal that the intersection of L and L orthogonal will be an empty set. Now also one part is simple, that is L is clearly a subspace of H and L orthogonal is also another closed subspace of H. So we can say that if we take the direct sum also, the elements in the direct sum of L and L orthogonal will also be contained in H. So this part is clear by the definition of L and L orthogonal and the definition of direct sum. Now we have to do the reverse inclusion, and once we do the reverse inclusion, we can prove the theorem. So for that we shall show that H is contained in L direct sum L orthogonal. Okay, so for that what we are going to use is, we will use proposition 2.2.2. So just recall that proposition what we did in the last section. We had seen that if L is closed subspace, okay, if L is a closed subspace, then we can always find a unique y such that x minus y is orthogonal to L and y equal to PL of x, that is y is the projection of the element x in H. So this was the proposition 2.2.2. so now let's see how we can utilize this here to prove this theorem. So we know that if we take let x be any element, any arbitrary element in H, then we can write x as x is equal to x minus y plus y, right? Why? Because just adding and subtracting y, we can write x is equal to x minus y plus y. Now by the previous proposition we have stated that x minus y is orthogonal to L and y was the element of L. Now x minus y orthogonal to L implies x minus y is an element of L orthogonal, right? So if we choose x minus y or choose z1 to be x minus y and y1 to be y, then we can write any x as the sum of z1 and y1, right? Where z1 is an element of L orthogonal and y1 is an element of L. So any element of H can be written as the sum of one element in L orthogonal and the other element in L. So which clearly implies that x will be an element of L direct sum L orthogonal. Therefore, as x was chosen to be arbitrary, we can conclude that H is a subset of L orthogonal direct sum L. So from these two inclusions we can conclude that L direct sum L orthogonal equal to H. So this was the proof of the theorem that we have seen. Now the proof was very much simple. We just had to use the proposition which we had done earlier, and the proof is very quite simple. Now next, what I want you guys to do is, I had mentioned, or I had given you an assignment to do the exercise problems 9 and 10. They are practically the same as corollary 2.2.5 and the lemma 2.2.7. both are the same. So what I want to do is, you have a weekend coming up, so just work your brains out and just try to solve the corollary 2.2.5 and lemma 2.2.7, which is same as the assignment that I had given you in the earlier class. So with this, we shall wind up with section 2.2, and we shall stop for today. That's it. Thank you. Stay home and stay safe.